Section 1.9, Inverse Functions. Verifying inverse functions. Before we talk about how to verify functions or inverses, let's make sure we understand what is an inverse function. So if f of x and g of x are inverses of one another, then the following is true. The domain of f of x equals the range of g of x and vice versa. Well, I'm afraid I didn't give you a super interesting example for our first example because the domain and range of this function is all real numbers and the domain and range of this function, which is linear, is all real numbers. So nothing too exciting happening there. Next, the function f of x would undo the function g of x and vice versa. So let's take a look. For f of x, it appears we're subtracting 2 from x and dividing by 4. Here we're adding 2 to x and multiplying by 4. So those do seem to be undoing one another. If you compose f of g of x or g of f of x, the result should be x either way. Let's double check. First, we're going to take f of g of x or f of 4x plus 2. So in my f of x function, I'm replacing x with 4x plus 2. And then I have minus 2 divided by 4. We'll simplify. Plus 2 minus 2 cancels. That gives me 4x over 4. The result is x. Let's go in reverse. G of f of x. So g of x minus 2 divided by 4 would be 4 times x, which is x minus 2 divided by 4, and then plus 2. The 4's will cancel. That gives me x minus 2 plus 2. Those cancel. I get x. If I take a look at the graphs, let me get rid of all of this. If I take the look at the graph of f of x and the graph of g of x, they will actually reflect along the line y equals x. So my greenish line here is the line y equals x. The sort of weird brownish colored line is g of x, which is 4x plus 2. And the blue line is x minus 2 divided by 4. And we can see that if I take this line and reflect it across the y equals x line, it does, in fact, reflect. So these are reflections of one another. And lastly, f inverse of x is equal to g of x, and g inverse of x is equal to f of x. That kind of goes without saying. We're saying if f and g are inverses of one another, I can take the inverse of f to get g and the inverse of g to get f, and so forth. So I only put that on there to point out what the notation is going to look like. When we're talking about an inverse, we say to the negative first power. And so don't get confused with a negative. It's not telling us to negate anything. It's telling us to take the inverse. The first thing we're going to do is just to verify that functions are inverses. And to verify them, I'm simply going to compose them to see if f of g of x is equal to x or g of f of x is equal to x. So let's do that. For my first example, I have f of 2 divided by x plus 3. So I'm going to replace x with 2 divided by x plus 3 minus 3 divided by 2. And I get, I'm just going to put f is equal. The plus 3 and the minus 3 do cancel out, so I have 2 divided by x divided by x. I'm sorry, divided by 2. And this now gives me 2x, 2 divided by x times 1/2. And my result is 1 divided by x. 1 divided by x does not equal x, and therefore, no, these are not inverses of one another. To verify that graphically, here's what this mess looks like. One function is f of x, that's the blue line. G of x is the brownish orangish line, and of course the green line is y equals x. And we can see that those do not, in fact, reflect across the x-axis. I'm sorry, reflect across the line y equals x. Let's take a look at our second example. F of g of x, so f of 2x plus 6 is going to give me 1/2 of 2x plus 6 minus 3. That gives me x plus 3 minus 3 by distributing the 1/2, which gives me x. And of course I can also check it in reverse, so g of 1/2 x minus 3 would be 2 times 1/2 x minus 3 plus 6. Sorry, I got confused which one was which. I distribute to get x minus 6, and then I have plus 6, and the result is x. So I have x each way, and these are in fact inverses. And again, you can see that I can reflect those graphs across the line y equals x. Finding inverse functions. Before we can find inverse functions, we need to know how to know whether or not a function has an inverse, because not all functions do have an inverse. However, if a function does have an inverse, that function is unique, which means there's one and only one inverse function. So in order to determine if the function has an inverse, we determine if the function is one-to-one. The definition of one-to-one, or the working definition, is that for each output there's only one input. So for every y there's only one x, and we can determine that using the horizontal line test. So for instance, we used the vertical line test to determine if a relation was a function, but the horizontal line test says if you touch more than one point, there is no inverse. So the function y equals x squared has no inverse, but this function, as we can see, I can draw as many horizontal lines as I want, and I'm only ever going to touch one point on the graph. Now let's work on finding the inverse functions algebraically. If you'll notice, I have two examples here, and I've already graphed those functions for you so that you can verify that these do both pass the horizontal line test, so they both do have an inverse. So that is always the first step that you should do, is to graph the function to ensure that your efforts are not in vain, that you can in fact find an inverse function. Now, because we know that the graph of the inverse reflects over the line y equals x, we can simply, in our function, replace x with y and y with x, or f of x, which is the same as y, replace that with x. And then we're simply going to solve for y. So for instance, my first function, f of x, which if you want to think of that, that's just y equals. I'm going to replace the y with x, and every time I see x, I'm going to write y instead. So 5y plus 1. Now it's just algebra. I'm just going to find y equals by manipulating the equation. So I'm going to start by taking each side times 5y plus 1. That gives me x times 5y plus 1 is equal to 3 minus 2y. I'm going to distribute the x, so that gives me 5xy plus x is equal to 3 minus 2y. I'm going to collect all of the values that have a y onto the left side, so I have 5xy, and I've got minus 2y on the right. I'm going to add 2y then to each side so that I can get rid of the 2y on the right. And I'm going to collect anything that doesn't have a y on the right side. So I have a 3 over here, but I need to get rid of this plus x, so I'm going to subtract x from each side so that everything is now in the correct spot. I'm now going to factor a y out of both of these terms, leaving me with 5x plus 2. And then I'm simply going to divide each side by 5x plus 2. And that leaves me with y is equal to 3 minus x divided by 5x plus 2. Now typically then you're either going to write this as y inverse is equal to 3 minus x over 5x plus 2, or you're going to write f inverse of x. Either way, it's correct. Just pay attention to whether it asks for function notation or not, but this is in fact a function. Graphing the new equation, the inverse function of 3 minus x divided by 5x plus 2, as you can see, does in fact reflect the original equation across the line y equals x. The second example, much easier, a lot less math. Again, I'm going to replace g of x, which is really y, with x, and I'm going to replace x with y and solve. So I'm going to square each side because that's what I have to do to get rid of a square root. And so I have to say x squared is equal to y plus 3, and then subtract 3 from each side, so I have x squared minus 3 is equal to y. So I would write that as f inverse of x is equal to x squared minus 3. However, this one's a little trickier. Easier math, but trickier concept, because if you'll notice, I only have 1/2 of a parabola here. I don't have the other half of this parabola. So I only need the function where x is greater than or equal to 0. So my inverse would be this function where x is greater than or equal to 0. Up next is the last section of the very long chapter 1, which is 1.10 mathematical modeling and variation.